Going over an analysis of a CubeSat's system requirements using FreeFlyer. So, a quick introduction to the team that worked on this. It isn't a one-man show. My name is Michael Harrigan. I'm an aerospace engineering master's student at the University of Illinois in Urbana-Champaigns. I also work in the laboratory for advanced space systems at Illinois. My professional skills are mostly systems engineering. My advisor, Dr. Michael Lembeck, is a clinical associate professor here. He's also the Laboratory for Advanced Space Systems lab director. He focused on the program management side of this mission. We also have Isabel Anderson and Christopher Young, two aerospace engineering master students who also contributed to the systems engineering and orbital mechanics of this mission. A quick overview of our lab space. We host a variety of testing capabilities, including thermal vacuum, MOICG, have a giant clean room, and a nice mission operations room. So a quick overview of the CubeSat that we'll be looking at today. The CubeSat's name is LASSI. It has two payloads on board. First, a set of photometers, which measure variations in nighttime air glow brightness. They're going to operate in the eclipse side of the orbit, and they have to be pointed within 10 degrees of nadir. The second payload we have is the retarding potential analyzer and neutral pressure instruments. These are going to measure plasma density, ion temperature, ion velocity, and neutral gas pressure. They're going to operate continuously throughout the orbit, and they have to be pointed within or at the RAM direction. So the goal of these two payloads are to make observations where you want to systematically observe gravity waves in Earth's atmosphere with large vertical wavelengths at lower F region heights. We're then going to correlate this data. We're going to correlate the atmospheric gravity wave measurements in the mesosphere to in situ measurements of ion and neutral density fluctuations. And then we're going to map, produce global maps of active gravity wave regions in mid and low latitude ionosphere. So, problem statement. We need to generate requirements for these things. So we have a set of payloads. We want to get them into orbit. We have to decide on a set of requirements to design the CubeSat around. For this presentation, we're going to be focusing on the power and communication subsystems and the requirements that go into that. Specifically, we're going to focus on power generation, power storage, and the radio specification. On the right here, you can also see a mocked up image of what we believe the satellite will look like, as well as the location and pointing direction of the payloads. So our methodology to incorporating FreeFlyer into generating these requirements. The first step is adding the spacecraft with the physical properties. For this, we're going to be designing a 6U CubeSat. We set the mass, center of mass, and moment of inertia based on some of our previous missions that are comparable. We set the central body. For this mission, we'll be orbiting around Earth. We set the available bodies. Just for simplification purposes, we are only using the sun, the Earth, and the moon. We planned to have this launch in first quarter of 2025. So we set the epoch date of January 1st of that year. We then set the element types and the propagator. We're going to use Keplerian element types, and we just threw it in an ISS orbit with a 1 second step size. We are then going to set our ground station location, since we're going to focus on the communication side of this too. We threw our ground station on the UIUC main campus with a 10-degree minimum elevation. We then have to script FreeFlyer to collect all the information we want. We set flags to determine the operating modes based on conditions such as in shadow, whether the satellite is in the shadow of the sun or not, or of Earth from the sun. Data storage and power storage levels are integrated based on the time step and what flags are currently triggered. If the payloads are active, then we should be generating more data, for example. Here we can see a little simulation of what some of the results we had look like. This is what it looks like while it's collecting the data. We wanted to be able to visualize to make sure that we're pointing in the correct directions, that the solar panels are actually pointed towards the sun, and to ensure that the payloads are operating as expected. And once we run the simulations for a few different configurations, we can make an educated decision on what configuration we want to go with. We looked at, for the power subsystem, 3 different configurations. We looked at a single deployable, single battery pack configuration. We looked at a double deployable, double battery pack with no sun tracking configuration. And we looked at a double deployable solar panel and double battery pack with sun tracking configuration. The exact stats of what the single deployable solar panels versus a single battery pack versus the doubles of them can be seen in that configuration column. But the main findings, and we're going to go into a little bit more detail about them here, is that the double deployable double battery pack with sun tracking is the only configuration that would suffice for this mission. So looking now at the more detailed version of the results, you can see from the summary table in the upper right-hand corner, the RPA and PI payload only has about an 18.7% payload availability, while the photometers will never actually operate due to our desire to stay above a 20% depth of discharge in our batteries. You can see the baseline value of the bus and with little spikes from the RPA and PI payload, with the largest spikes here being communication sessions, since our radios draw a significant amount of power. The main finding was, based on this, that we're going to need more batteries and more solar panels to operate both payloads on a regular basis. So now looking at the double deployable solar panel and double battery pack with no sun tracking configuration, the numbers look a lot better, with 85.4% payload availability for the RPA and PI payload and a 96.04% availability for the photometers. You can also see on the right here now, the power usage is a lot more stable because the payloads have significantly more uptime while still having the occasional communication session. We're also staying well above our depth of discharge line when you look in the short term, the 2-day long simulation. Looking at the 1-year-long simulation that you see on the left-hand side, though, you can see a notable problem of a few points throughout the year. We measured 4 for this simulation, where the panels become edge-on with the sun. They become parallel with the sun's rays, essentially, resulting in no power being generated. This occurs due to RAN and us basically tracing the terminator line around Earth throughout the orbit. At this point, because the sun's not generating any power, the satellite would die. So for this final iteration, we decided to include some sun tracking to make sure that we can actually generate power throughout the full year. With the sun tracking, the payload availability increases to 100% for both the RPA and PI payload and the photometers. You can see in both images we're well above the depth of discharge, and payload operations and bus operations remain at 100%. So for the power subsystem, we decided to write the requirements that we need. The system shall have sun tracking. The system shall have double deployable solar panels, and shall have a double battery pack based on the watt generation and watt hour storage that we had outlined in the previous slides. Looking at the communications subsystem now, we looked at only one configuration, and thankfully it met our requirements. We looked at our S-band radio with a 3.3 megabyte downlink per second, and which consumed 13.3 watts while transmitting. Here we have both a 1 month long and a 2 day long simulation. You can see in the 2 day long simulation that we're using approximately 48 megabytes worth of data. And we can store all the data necessary within 128 megabytes of data storage. Looking at the 1 month long side of things now, we use approximately 7 days to get all the data down. This varies slightly throughout the month, but when looking at the year-long thing, this data was pretty comparable. Based on that data, we know that the S-band meets our requirements, and the requirements we wrote as a result are that we shall have at least 3.3 megabytes of downlinkable, or the communication subsystem shall be able to downlink 3.3 megabytes of data per second while transmitting. So just looking at FreeFlyer's Impact now, for this LASSI's CubeSat development, it started with an idea of incorporating these two payloads into one new spacecraft. We then go into the planning stages of identifying the different subsystems and what performance metrics we need to write requirements for. We then do our development in FreeFlyer, writing scripts that collect specific outputs to determine the requirements we're looking at. We're then going to plot the results. All the data from FreeFlyer has been plotted in the charts that we saw earlier. We can then present these plots in our mission design reviews, which we can then take into our proposals and land contracts with. So I'll take questions now. Before that, if you have any questions about our program or the lab, you can contact me at meh4@illinois.edu. We also have a phone number on there, and you can follow our lab page at UIUC_AE_LASSI on Instagram. The QR code will also take you to our blog, which hosts additional information about different programs we have going on within the lab. One more thing, thank you to FreeFlyer for hosting us today. And while I showed just one example of the type of CubeSat missions we have, this same process we've used for numerous missions, and it has been a lifesaver for us compared to doing a lot of back of the napkin type of calculations and trying to write requirements based on that. So thank you. I'll take any questions that you all have now.
Excellent. Great job, Michael. We do have a couple of questions in the chat. So the
Okay.
first one is from Chaitanya, actually. What were the challenges you faced using FreeFlyer for this analysis, if any?
Well, the documentation for FreeFlyer is outstanding. I've had a lot of experience using FreeFlyer, starting in my senior design course. I'm now a second year master's student, so I've been using it for the past 3 years, essentially. Um, the biggest challenge for this mission in particular um, was probably doing some of the attitude control aspects of it. And by no re or yeah, that's no fault on FreeFlyer. That's just my personal struggles with attitude determination and control. Getting a nice slew going, and especially animating it versus just having it jump, was my biggest struggle with this particular mission.
Great. Jesus asks about the lab. Is manufacturing done in-house for these projects?
It depends on the component and the subsystem. Some things we do in-house, some things we go out of house for. We do have multiple machine shops on campus, so a lot of the things we can do on campus, depending on the level of precision necessary.
That sounds awesome. And then Holger asks, as you measure ions and plasma characteristics around the spacecraft, did you consider to calculate the spacecraft's own electrostatic potential against space?
Yes, we have, in fact. This was one of the main points brought up during the design review of this mission. It's something we don't have the best solution for at the moment, but it is definitely something we are aware of and working towards.